In the Langmuir model, we assumed that catalytic surfaces were made up of identical non-interacting sites. So our catalytic surface might look something like this, where we have a fixed number of sites that are all identical and all don't interact with one another. So in reality, we know that this is not the case. So we have catalysts that might look something more like this on the right, where we have a supported nanoparticle catalyst. And on this catalyst, we're going to have atoms that have varying coordination. So whether they're on different types of crystallographic facets, or whether they're on the edges or steps of these catalytic surfaces, their properties are going to vary. So what we could say is the Langmuir model essentially assumed we had a catalytic surface that behaved in this way. If we look at the heat of adsorption, or the negative of the enthalpy of adsorption versus coverage, it was fixed until we got to a coverage of 1. So until we got to the point that we filled up all our surface sites, and then no more adsorbate could be added. So the question we want to think about here is, what does this heat of adsorption versus coverage profile look like for non-ideal or real surfaces? So what we could do to treat non-uniform surfaces mathematically is to divide the surface into a number of Langmuirian type ensembles, which are populated according to their adsorption energies. So let's look at how this works. So we could say that the coverage of some species A would be equal to the fraction of the surface with some adsorption energy, which we'll call Fi, times the coverage of those types of sites. And so we'll sum over all the different types of adsorption energies that we have on the catalyst. So what might this profile look like for the heat of adsorption, so minus delta H of adsorption, versus coverage? So what we're saying here is that there's different fractions of the surface that have different fixed heats of adsorption. So there's different sort of populations of the surface that behave like Langmuirian surfaces. So let's say we have one fraction, which we'll label F1 here, some fraction of the surface that has one fixed heat of adsorption, we'll label 1. Then we'll have maybe some other fraction of the surface that again has a fixed heat of adsorption but a different heat of adsorption, so we can label it minus delta H of adsorption 2. So we'll label this F2, and so on until we populate the entire surface. And so to calculate the coverage, each one of these fractions of the surface, that theta AI, is going to act like a Langmuir isotherm. So it's going to be KAI PAI over 1 plus KAI PAI. And so we'll sum over all of these different fractions of the surface that have these different adsorption energies. So that's a sort of approach where we lump the surface into these discrete fractions that each have constant heat of adsorption. Alternatively, we could express the variation in adsorption energies as a continuous function. So we can define some function g of q, where q is the heat of adsorption. You'll often see it denoted this way. Q is heat of adsorption. So that's equal to minus delta H of adsorption. So what this function gq dq describes is the fraction of the surface that has a heat of adsorption between q and q plus dq. This also means that this is a normalized function, so if we integrate from 0 to infinity, gq dq, this will equal 1. So what this allows us to do is to write the coverage of A as the integral from 0 to infinity of essentially a Langmuir isotherm times g of q dq. And you can note here that k is going to be a function of q. So of course we can write that theta A is equal to, each k is going to be equal to e to the minus delta g of adsorption times RT. So we can write the entropic contribution as just a prefactor, k naught. And we can write this depends on e to the minus delta h over RT, or just e to the q over RT, times the pressure of A over this denominator, k naught e to the q over RT PA. And so now you can see that this Langmuir isotherm part of our expression is also a function of q. So that's how we can solve this mathematically if we have some functional form for g of q. But what is this functional form? So how does the heat of adsorption depend on coverage? So different models for g of q have been used historically. We won't go through all the different ones, but the most common is what's called Temkin's model. And what this says is that the heat of adsorption varies linearly with coverage. So the heat of adsorption at any coverage is equal to the heat of adsorption at zero coverage times this linear function, 1 minus alpha theta. So experimentally, it's also frequently observed that the Langmuir model describes coverage quite well to a certain point, after which further increases in coverage are accompanied by a steep drop in the heat of adsorption. So this is due usually to adsorbate repulsion, so these adsorbates interacting with each other on the surface, rather than surface non-uniformity. So this is conceptually how we can treat non-ideal adsorption on catalytic surfaces, and some ways mathematically that we can do this by treating the heat of adsorption as either a discrete function with different fractions of the surface having different heats of adsorption, or as a continuous function where the heat of adsorption changes continuously with coverage.